Today, we are diving deep into something absolutely fundamental to the modern internet, microservices architecture.
Mm-hmm.
If you're using almost any huge application today, think Amazon, Google, Netflix, you're dealing with systems built this way. Systems broken down into, well, thousands of tiny moving parts.
It was pretty mind-boggling when you think about the scale.
Right. So our mission here is really to shortcut that learning curve for you. We want to trace how we got here, why application design had to change so drastically.
Yeah, understanding the why is crucial.
And explore what microservices really mean philosophically.
Yeah.
But also, and this is key why it's not some magic fix, it trades old problems for new, really complex distributed ones.
Exactly. And managing that new complexity requires a whole arsenal of tools. It's a fascinating evolution.
It really is.
Yeah.
So where does this story start? You mentioned complexity.
Well, it always starts with complexity, doesn't it? Over the last couple of decades, applications just exploded in size and scope.
Exponential.
Totally. And the fundamental engineering way to handle complexity, you break it down. Decomposition, smaller, manageable chunks. That simple idea is what pushed us away from the starting point.
The starting point being the monolith. Let's quickly touch on that because its failures really set the stage.
Right.
So for anyone not familiar, picture the early web apps. Everything, the website you see, the business rules behind it, the database access, all bundled together.
One single giant piece of code deployed all at once.
Seems simple enough to start with, right?
Oh, yeah, very straightforward initially. But that simplicity hides a trap.
The trap being?
Maintenance and change. As soon as that application got big and you needed to update things quickly, oh boy.
Nightmare.
Pretty much. Everything's tangled. A tiny bug fix in one part meant you had to rebuild, retest, and redeploy the entire massive thing.
Which is slow. And risky.
Terribly slow. Incredibly risky. And forget about scaling large teams working on the same giant code base. Just constant collisions and integration problems. It just couldn't last.
Okay, so the monolith breaks down under its own weight. What was the first real attempt to fix it?
That led us to what's usually called multi-tier architecture. The idea was, okay, let's not have everything mushed together. Let's separate things based on their technical job.
Like separating the visuals from the logic.
Exactly. The most common pattern was the 3-tier architecture. You'd have a presentation layer, the user interface.
What the user actually sees and clicks on.
Right. Then a logical layer or business logic layer. This had all the rules, the processes, the calculations.
The brains of the operation.
Sort of, yeah. And finally, a data layer responsible for talking to the database, storing, retrieving data.
That sounds much cleaner. Separating concerns.
It was cleaner, definitely an improvement over the monolith for organizing the code itself. But there was a catch.
There's always a catch. What was it this time?
It was still centralized. Even though you separated the code logically, you often still deployed the whole thing, or at least large chunks of it, together.
So the deployment unit was still big and monolithic in a way?
Pretty much. If you needed to update the business logic tier, it was still often a big coordinated release. It helped with code structure, sure, but it didn't solve the operational independence needed for really fast-growing, complex systems. Think about the scale of Amazon or Google's search engine back then.
They needed something more radical.
They needed a genuine paradigm shift. The sheer scale demanded it. We couldn't just separate technical layers anymore.
So we needed to break things apart differently, not by technical function, but by something else.
Exactly, by business capability. That's the absolute core idea of microservices architecture.
Okay, unpack that. What does business capability mean here?
Instead of one big logical layer handling, say, user profiles, product catalogs, inventory, and payments, you break each of those out.
Into its own little service.
Precisely. You have an inventory service, a customer account service, a payment gateway service. Each one is totally independent and focuses on doing one business thing really well, end to end.
End to end meaning.
Yeah.
It handles its own logic and its own data.
Yes. That's crucial. Each microservice typically owns its own database or data store. It doesn't share it directly with others. It operates independently. It's like applying domain-driven design principles to the architecture itself.
Okay, I can immediately see the organizational win there. My shopping cart team can just work on the cart. We can deploy updates whenever we want.
Without even talking to the user authentication team, potentially.
We don't block them, they don't block us. That must speed things up incredibly.
That independence is the primary driver.
Yeah.
And how do they talk to each other if they're separate?
Through APIs.
Yep. Simple, well-defined APIs, usually lightweight stuff like standard HTTP calls or maybe using message queues for asynchronous communication.
And because they're independent, theoretically, different teams could use different technologies. Like one team uses Java, another uses Python.
Theoretically, yes. That's the dream, right? Pick the absolute best tool for that specific job. Freedom.
But you said theoretically. The real world kicks in, I assume.
Oh, it kicks in hard. Imagine the chaos and cost if every team truly picked any language, any database, any cloud provider they wanted.
Yeah, operations would be impossible and expensive.
Astronomical. So in reality, most organizations say, okay, freedom is great, but for efficiency, maintainability, cost reduction, you need to choose from this approved list.
A curated tech stack, standardized tooling. Makes sense.
It's a necessary constraint. But this brings us to the really interesting part, the flip side of the coin.
The downside.
The downside. You solved the complexity inside the big application block by breaking it into small pieces. But you didn't eliminate complexity.
You just moved it.
You exchanged it. You traded application complexity for operational complexity, the complexity of managing a highly distributed system.
Yeah.
And that's where things get hairy.
Okay, let's get into that. If these services are small and independent, where's the big danger? It seems like failure would be isolated.
Ah, but they talk to each other, remember? They depend on each other's APIs to get work done.
Right, so if one fails.
If one critical service fails, say the inventory service gets overloaded during a big sale, then the product catalog service might start failing because it can't check stock levels. The checkout service might fail because it can't confirm inventory before charging the customer. The recommendation engine might fail.
It ripples outwards, a cascade.
Exactly, a cascade of outages. One small failure can trigger a chain reaction that takes down large parts of the user experience.
And because everything is distributed, finding the source of that original failure must be tough.
Monumentally tough sometimes. The user sees an error on the website, maybe generated by the checkout service, but the root cause might be 3 or 4 service calls away, deep inside the system, maybe a slow database connection in the inventory service.
So debugging becomes a forensic investigation across multiple systems.
You got it. Identifying the root cause quickly, under pressure, in a system with potentially hundreds or thousands of moving parts, that's the new grand challenge.
Wow. Okay, so if it's this fragile and hard to debug, how on earth do companies like Netflix actually run these things reliably? They must have built something else.
They absolutely had to. The engineering community basically invented a whole new ecosystem of tools specifically to tame this distributed complexity. You can't do microservices at scale without them.
The supporting infrastructure. The heavy artillery, as we called it earlier.
That's a good way to put it. There are several key categories of tools you absolutely need.
Let's break those down. What's piece number 1?
First, you need a standard way to package and run these services anywhere. That's containerization.
Like Docker.
Docker is the prime example, yeah. It lets you bundle your microservice code, all its libraries, everything it needs, into a lightweight, self-contained box, a container.
So it runs the same on my laptop as it does in the cloud.
Exactly the same. Consistency is key. That solves the works on my machine problem.
Okay, so now I have thousands of these neat little Docker boxes. Who manages them all? Starts them, stops them, replaces them if they break. You can't do that manually.
Absolutely not. That requires the second critical piece. Container orchestration systems. The big one here is Kubernetes.
Ah, Kubernetes. Hear that name everywhere.
For good reason. Kubernetes is like the brain or the conductor for all your containers. It handles deploying them onto servers, scaling them up or down automatically based on traffic.
Auto-scaling, nice.
And critically, automatically detecting and replacing failed containers. That self-healing capability is vital for resilience against those cascade failures. It also manages networking between them.
So Kubernetes keeps the fleet running and healthy. Got it. What about getting the code into those containers in the first place, if teams are deploying independently all the time?
That needs serious automation. Piece number 3, pipeline automation, usually called CI/CD, which stands for continuous integration and continuous deployment.
Right. Automated build, test, deploy pipelines.
You need them. If you're potentially deploying dozens or hundreds of times a day across various services, it has to be automated, standardized, and safe. Fast, reliable deployments are crucial.
Makes sense. Okay, containers, orchestration, deployment pipelines, what else? How do the services talk reliably without creating tight dependencies?
That brings us to piece number 4, asynchronous messaging systems.
Like message queues.
Exactly. Things like RabbitMQ or Kafka. Instead of service A making a direct call to service B and waiting for a response which couples them together and can cause slowdowns if B is busy.
Service A just drops a message onto a queue.
Right. Service A posts a message like, hey, process this order to a queue. Service B picks it up and processes it when it's ready, maybe sending another message back later.
So they don't have to be available at the exact same time. More decoupling?
Much more decoupling. It improves resilience and responsiveness. Service A isn't blocked if service B is temporarily slow or down.
Okay. Containers, orchestration, CI/CD, messaging. We're building a robust system. But you said failures will happen. How do we see what's going on when they do? How do we trace that failed request through 50 services?
That's the fifth and arguably the most critical piece for day-to-day operations. Monitoring and logging. You are flying blind without it.
What kind of monitoring are we talking about?
Specifically, you need strong application performance monitoring (APM) tools. These tools understand distributed systems. They provide distributed tracing.
Distributed tracing.
Yeah, it means when a request comes in from a user, the APM tool injects a unique ID that follows that request as it jumps from microservice to microservice.
So you can see the whole path.
You can see the exact path it took, how long it spent in each service, which service returned an error, where the bottlenecks are. It's like an X-ray for your distributed system.
Absolutely essential for debugging those cascade failures.
Couldn't do it without it. And alongside APM, you need robust centralized logging. All your services need to send their logs to one place so you can search and correlate events across the entire system when troubleshooting. Visibility is everything.
Wow. So Docker, Kubernetes, CI/CD, message queues, APM, logging.
Yeah.
It's a whole complex ecosystem just to manage the complexity we created by breaking things down.
That's the irony, isn't it? We decomposed the application to manage complexity and ended up needing a complex infrastructure layer to manage the decomposition.
It really highlights that there's no free lunch in software architecture, especially at scale.
Not at all. And that leads us to the final, really crucial takeaway here, the big caveat.
Vicious.
Microservices are not a silver bullet. They are not the right answer for every problem.
Right. The sources emphasize this.
They solve certain problems, particularly around organizational scaling and independent deployments, but they introduce significant operational complexity. That tool chain we just discussed, it's not trivial to set up and manage.
So for many applications, the old ways might still be better.
Absolutely. If you have a relatively simple application, maybe a small user base, something that isn't evolving at lightning speed with dozens of separate teams, a monolith, or maybe a well-structured multi-tier app, is often still the correct, simpler, and cheaper choice.
Don't introduce the complexity of distributed systems unless you actually have the problem that distributed systems solve.
Precisely. Remember, highly distributed systems are hard. Really hard.
Okay, so summing up for everyone listening, we went from monoliths, which were simple but tangled and hard to scale, to multi-tier, which cleaned up code but was still centralized. Then the need for speed and scale drove us to microservices, breaking things down by business capability for independence.
But that independence came at the cost of operational complexity, needing a whole ecosystem of tools like containers, orchestration, and monitoring just to keep the lights on.
So here's a final thought to leave you with, something to mull over. If the core challenge shifted from application complexity to managing distributed operational complexity, especially those cascading failures, and we've kind of pushed decomposition about as far as it can go, what's next? Could future shifts focus less on how we break things down and more on building infrastructure that's smarter? Infrastructure that can perhaps predict failures or automatically isolate and fix problems before they cascade almost instantaneously.
Interesting. Smarter, self-healing, maybe even preventative infrastructure.
Maybe less about the architecture of the pieces and more about the intelligence of the platform holding them together. Something to think about.
Definitely something to chew on.